All right, good morning, everybody. We're starting just a few minutes later today because, outside. All right, and also I'm trying to set up so that we actually do this recording properly, because last time yours truly did not activate the podium projection, so the diffusion demo didn't record properly. But I think we're in business now. So let me just do that. 1, 2, 6, 6, 2, 1. Okay, fabulous. Okay. Okay, let's see. Built-in microphone. We're going to record. This person. All right. Present content. Okay, looks like we're just about live. Okay. Okay. Slowly but surely, everybody. Okay. We finally got that working. So today, as you've seen with the iron phase diagram demo that I sent out, we'll be talking about iron phase transformation. So we talked about polymorphism already at the beginning of chapter 9. We talked about iron going from BCC to FCC back to BCC again, going from alpha to gamma to delta phase, right? And these phases have different names. They're ferrite, austenite phases. So that's what we'll see today as soon as Paul is done setting up. And we can project it. So what Paul's setting up right now is a piano wire that's a 12 gauge. And so what we're going to do is resistively heat this wire with this variac. So it's AC current. And he's going to do it very safely because we're going to get the temperatures up to the phase transition temperature, which, as you recall, is what for iron going from BCC to FCC? Okay, that's the Curie temperature, so we'll talk about that. Thank you for pulling up the slide. Okay, so let's see. Let's record. Okay, I think we're basically there. See? Okay. Now I'm just going to adjust my webcam, aka my wonderful iPad, real fast so that it can capture the height. Okay, that's about right. It's good. Now that we have 3 computers, there's more computers than people presenting. That's when you know it's too cluttered and this needs to be streamlined better. Okay, so, okay, hold on. Are you just?
I'm heating it up so it kind of relaxes
before
we get the phase transition.
Okay, thanks. Okay, let me turn on the screen then. Okay. Let me pull up the demo slide. Right. So this is what you see so far. Okay. Right. So what Paul is doing is he is resistively heating up this wire. And so we're just going to heat this up. Oh, thank you. It's in the box right there. There are two types of magnets. There's this one, and then there's also this one.
Okay.
Yeah, either will work. And what we're going to try to do is try to catch it so we don't burn
Yeah, I'm gonna have
this
to
table.
tap in back just a bit.
Yeah, okay. Great. Okay, so those in the front can probably smell or see the smoke that's coming off of this wire. It doesn't smell great. Usually wire is stored with, iron is stored in some sort of oil so that it doesn't rust. And as you know, iron oxide becomes quite brittle. Do you want to apply it?
Yeah.
Oh, hold on.
Oh, it's inside?
Yeah.
Oh, here we go.
So why don't you
Is
just
this-
attach it? Just take one and attach it.
Okay.
Yeah. Or you can use one of the other. Yeah. Also, don't touch this because, you know, we're running electricity through it, and, you know, self-preservation, I hope, is high. So,
So pop this on.
yeah, either that or this.
I like that.
Okay, all yours. Okay, so there you go. So Paul has, let me take a photo so I can post this for you all later on. Okay, so it's hard for you to see, but there's a magnet on here. So iron is ferromagnetic. That means all the spins are aligned, right? So we have something like this. So now it's continuing to increase. Apply, well, this goes up to about 12 amps or so. So we're not going to short circuit this room, and we won't have to evacuate and make the classics department very mad at us, at least not today. Okay, there's a weight in the middle just for visualization. You can also look at the graduated cylinder because it's demarcated, so that's helpful to see. So as you can see, okay, do you see how the wire is now sagging a little bit? Okay, what do you think is happening there as the wire is now heating up resistively? What causes this sag? It's still sagging. So it was once before up here, the weight, and now it's coming down. So what is happening to the length of the wire? I saw a hand here. So Eddie says it's thermal expansion, right? As we've seen from chapter 2 with the energy versus atomic bond radius, E versus R plot, right? With thermal expansion, the average R increases as you're putting in energy, as you're increasing the temperature, right? Your average bond distance is increasing, so your material is expanding. There's the same number of atoms. We haven't done anything. There's conservation of mass. There's nothing special about this other than the fact that we're heating up the material and it's thermally expanding. Now, as he's increasing the voltage, what do you see in terms of the color of the wire? It's glowing red, which means one should probably step back, okay? So you can see it's getting hotter. So this is incandescence, right? This is how your light bulb works, essentially, right? But as we're doing this red hot optical change should also be indicative that iron is now oxidizing to iron oxide. So the metal is becoming a ceramic. And in general, that's a very bad thing if you're aiming for ductility, right? Because now the material is becoming more brittle. Okay. So Paul has just killed it. So now it's cooling down. Interestingly enough, though, the magnet has not dropped. So that means we haven't approached the Curie temperature yet. We haven't reached 770 C, which is on your slide, but also what Zachary said, right? So that means now the material is still ferromagnetic. The spins are still aligned. As soon as you go above 770 C, that's when the material becomes paramagnetic. The spins are still there, but now they're not all aligned anymore because you've just heated up the material. So the magnet should drop. So the magnet still being there is telling me that right at that spot is not 770 C. The rest of the wire could be 77 C, but right at that spot is not 770 C just yet. And you can see that the magnet is actually it's also itself either a metal or a ceramic, right? So it also is absorbing all that heat. So maybe the rest of the wire is still being heated up, but right there, it's not 770 just yet. So Paul's going to continue until we reach 770, and hopefully we'll reach 910 soon. You kind of have to apply maybe 50.
You
Yeah.
can do it slowly or it could break the circuit.
Yeah, there's that. It's glowing a lot. It should be glowing a lot. I don't know. Okay. All right. Okay, it's very obvious now. Okay, but the magnet still hasn't dropped. We haven't achieved 770 yet. So it's now just thermal expansion. There's no phase transformation, okay? We're still in this region right here, okay? So I'm just going to switch very briefly over to output, just so the back can see a little bit better. So we'll see about Thank you very much, Paul. Fabulous. Yeah, so we're right here, okay?
So BCC is shorter than FCC, correct?
What?
So BCC is shorter than FCC.
No. BCC atomic packing fraction is 0.68. It's going to expand. It takes less, right? FCC is denser, so you can pack more into the same amount of space, so it's going to shrink.
Okay, but with the wire sag, isn't it extending, not shrinking?
Yes, but that's thermal expansion. So when you haven't gone through the phase transformation yet, before when Paul was just starting to heat up, that's BCC, heating BCC, heating to more BCC. That's just thermal expansion. So it's a convoluted mechanism that you're seeing. Okay, let me turn off this real fast so I can switch back and forth. Okay, so I'm going to exit this meeting. I'm going to kill the meeting real fast. Okay, so that's recording. All right.
It's also covered in iron oxide. Like if you run your finger through it, it gets, I don't know, you probably can't see that, but
Yeah.
it's definitely a lot of black stuff on the surface.
Right, and so if Paul had heated, cooled a number of times, as he said, you would have made more iron oxide, and thus it would have been brittle. And then if you just take it, you can actually snap it pretty easily. Okay. All right, that's working. So we're going to leave that to work so that we can get back. So the whole point of this demo is, 1, thermal expansion, 2, optical properties are changing. You're seeing changes in magnetic properties because of heating up a material, and then eventually you see an actual phase transformation. Granted, it's a really subtle, going from BCC to FCC is actually kind of difficult to see when it's not compounded with also thermal expansion. So, so that was that. Okay, let me see. That is converting. That's working. Let me go back. Okay, the only thing I need left is this guy. Okay, we'll see if we need this today. There we go. And great. All right, let me put this and this. Okay. Okay, now it's loaded back up. All right, so let's pick up where we left off last time while Paul is cleaning up. All right, so last time we were talking about Gibbs phase rule. All right, so we were talking about Gibbs phase rule, and we wanted to know how many degrees of freedom we have in each phase field. Okay, so here we're talking about a liquid portion, so that's L here. We have a solid region, so below this line, this solidus line is the solid region, and above the green liquidus line is all liquid phase field, okay? So here in your book, they've already calculated some of the degrees of freedoms in the various phase fields, okay? So here you have, if you're in the liquid region, you have 2 components, right? You have component A and component B. So that's 2. How many phases do you have? You just have 1. That's your liquid phase right there. And here, you're just increasing or decreasing temperature. So you only have 1 non-compositional variable, okay? Obviously, you can change the composition, but then you're changing the chemistry. So we're not talking about that. We're just talking about non-compositional variables, temperature, pressure, things like that, okay? So if you're just changing temperature, that's the 1. And so then you have 2 degrees of freedom. So that's what's telling me is in this region, you can move this way, you can move this way. It doesn't really matter. You're going to be in that, you're still going to be liquid, okay? Then there's what's called an invariant point. And you've seen this in your water, your H2O phase diagram, right? There's a triple point where both the solid, the liquid, and the gas phases all coexist. And if you change temperature or you change pressure, you're not going to have all those 3 phases in coexistence anymore, and thus it's an invariant point. Okay, you can also have an invariant line. It's called a univariant line. That's when you're here. Okay. And then, so we see that in H2O example, there's also an invariant point right here. So if you move off of that point, you're not going to have a coexistence of both liquid and solid. Okay. So what that means is you have, at this point here, you have 100%. If your composition is in weight percent, let's say, at this point B, right, you go from 0, nothing B. All you have is this component A. Then you keep on increasing B until you hit 100% B, and there's no A anymore. Okay, that's the line we're talking about right here. And similarly, over here, you have 100% A and 0% B. Right? So you have 1 component here. So that's why this is 1. You have two phases because you have a coexistence of the liquid phase and the solid phase right below. Thank you, Paul.
Yep.
And then you're still changing temperature. But here you see you have 0 degrees of freedom. You move off of that, you're going to be all liquid or all solid, but you don't have a coexistence of two phases. And so you're having an invariant point. That's when you have 0 degrees of freedom.
So what exactly is the middle space, like the white area?
Yeah, the middle phase of this isomorphous binary phase diagram launches us perfectly, Ethan. That's a great segue. What is that stuff in the middle? That stuff in the middle is a coexistence of both liquid and solid, but it's a two-component region. So here, right at these points, I'll redraw the points in blue. Okay, that's one component with two phases in coexistence. The stuff that's in the middle, that's liquid and solid, but it's two component. It's some mixture of A. So this line right here, they draw it at 50% atomic alloy. So here in the example, I have a time percent. Granted, for the purpose of discussion, it could be weight or, or atomic. It doesn't really matter. It's just very schematic right now. But here, if you have, let's say, 50 atomic percent, that means you have 50 AB. So your stoichiometry is something like this. It's 1-to-1. Okay, right at this dash line that I've drawn over in blue. That means AB coexists as some liquid and some solid, depending on the temperature. So if you're here, right, is there more liquid or more solid for this AB mixture? Versus if you're down here at a lower temperature. So that's what we'll talk about today, is actually quantifying that, okay? And so what's happening is you have this mixture AB right here, and then you're starting to cool. So every phase diagram, start from the top, cool down. You start from the top, you cool down, and at some point, okay, it's all liquid, and then you hit the liquidus line. It starts solidifying. You're starting to now form some solid of AB. And then you solidify some more, transform more of that liquid into solid, and then here, right here is when that solidification is going to go to 100%, okay? And right below that temperature, just like a degree below, you're going to get 100% solid, and now you're in the all solid region. Any liquid that you had will have solidified 100%. Okay. So this is an isomorphous binary phase diagram. What that means is morph, right? That's the crystal structure. So a good example is what you've seen before, nickel copper, right? They satisfy the Hume-Rotherham rules. They're both FCC. Electronegativities are very similar. Atomic radii are very similar. So they're just going to form a solid solution. You add in a little bit of nickel. Let's call that B. You add a little bit in. It's going to go into copper's FCC. It's going to be great. They're going to be very happy together. All is dandy. This is going to be the type of binary phase diagram that you see for these types of systems. Iso just means the same, right? Isobestic, isothermal, iso whatever, isotropic, it means the same, okay? Things get interesting when components don't exactly satisfy Hume-Rotherham rules, or they don't form complete solutions, okay? That's when things get very interesting, and that's when things get very useful for us. Okay, so I've summarized basically all of that. You have one component, let's say call it copper. You have a melting point of copper at about 1,100 C, say. You have melting point of nickel. There is much higher, it's about 1,450 C, okay? When you start mixing them together, I can tell you how much I mixed if I just tell you this binary phase diagram, and I say, look, if you add in 20% of nickel, and you're at 1,200 C, or maybe let's make it a little bit more egregious, let's say 1,150 C, you're going to be right there. So at that temperature and that composition, you're telling me, according to this phase diagram, that there's some precipitates. There's already some solidified copper nickel, okay, at 20 weight % nickel. And not all of it has solidified yet. That's all you've told me. But the fact that I can see this phase diagram, I can say, it's isomorphous binary phase diagram, so that means they're going to form this solid solution. It's going to mix very well. Great. I just have to wait for you to drop the temperature, and then we can have the solidified form. Okay. And the way people measure this is pretty standard. You stick a thermometer in there and you weight it out and you map out this phase diagram, which is great until your world becomes more complex. And then, as I mentioned, you can start taking and culling a database of all these energetic parameters, all these temperature values, and then you could start to make your own binary phase diagram, just computationally. So you could see if you measure the temperature as a function of time, you could see, okay, if you heat it up and then just let it cool with different composition, you could start to map out the phases. So you can map it out, and then when you say, okay, well, can I plot how much, if I wait a long enough time, how much has it solidified based on the different composition of my second component? And you could see, you can map it out really well. Okay, you just stick a thermometer in there and just wait. So it's really, it's a simple experiment, but that's because you have a simple system. But in theory, you could apply this to any complex systems as well. You just need a very good crucible and an isolated temperature bath, and you're good to go. Okay, so when you're given a blank diagram like this, immediately you should see the liquidus, the solidus, right? You could see, okay, where are the melting points of the single components, all right? Anything that's not L, as I mentioned in the last lecture, is a solid. And they have fancy Greek letters, typically starting with alpha for obvious reasons. And then, then you go from there. And you can obviously go all the way into the Greek alphabet. So just a review. 2 components, 3-phase field. Liquid, solid, some mixture. That's all it is. Okay. With isomorphous phase diagrams and any other phase diagrams, you can use it to look at the composition, so the number of components, the types of phases, the concentration, the amount of each phase. So that is actually an important part, and then you could apply the lever rule. So we're going to use the lever rule to quantify how much liquid is apparent at a certain temperature versus how much solid. Okay. So the way you do that is you draw a tie line, and that's something we brought up very briefly when we launched into chapter 9. Okay. So you draw a tie line, and you say, okay, I'm at 1300 C. Okay, great. So you actually don't draw that. That was actually a visualization. So you draw a tie line at that temperature. You say, okay, at this temperature, what am I going to see? I'm going to see some liquid. I'm also going to see some solid, but at this composition, let's say, okay, pedagogically, I think it'd be best to start from 50 and go up. So you could see at 50-50, at 1300 C, you're going to have more liquid or solid? Brave soul. Okay, revision. You're solidifying the entire compound. Yeah. So already, when I say 50-50, okay, that's a great point of clarification. When I say 50-50, that means I have 50% copper, 50% nickel. What I'm asking is, let's take this whole chunk. Okay, I've given you the composition, but let's take this whole compound, 50-50, nickel 1, copper 1, or copper 1, nickel 1. Usually you write the electropositive material first and the electronegative material second, typically. The more electropositive and the less electropositive material second. So what I'm saying is, how much of this copper nickel is still in liquid form, and how much of the whole copper nickel system is in solid form. So now I just lump them together. I've stopped treating them as single components. I've taken the whole system together now. Okay, so treat copper nickel as like one entity. 2 components, 1 material. Okay. So this is where our technical definitions of what a phase is, what a component is, comes into play, because it can start to get very confusing very fast. Okay, so schematically, if I'm at 1250 C, so here I've zoomed in, right here from this larger phase diagram. If I'm at 35 weight percent, first you have to know your composition. You have to know, okay, 35 weight percent, what does that mean? That means you're right here, okay? And if you're given a temperature, which you have to be given a temperature, if you're at 1250 C, now you can draw the tide line, and you could say, how much more, do I have generally more liquid or more solid at this composition and at this temperature? So you use the lever rule. Schematically, if you think about it as like a balance, right? And you say, okay, if this is supposed to be lighter. Let's say you have halfway through. They're not really, if I do this right, okay, also this is a very flexible bar that I grabbed from my shelf, so it's not the best example, but we're gonna do what we can. So in theory, you can change your center, right, based on the weight, as you recall from like a typical mass balance, a very old-timey mass balance, right, a fulcrum, say. Yeah, so that doesn't work anymore. So if you have something really heavy, right, versus something really light, you could see the center of mass is a little bit different, okay? So if this is weightier, that means you have more of this material, even though the distance is shorter, okay? Just torque, okay? Questions on that? No questions, or I don't understand? Or both. Okay, so let's review. You can, if you play around with your own weights, right, you could say, you can use two very different masses, and you can compare where your center of mass is going to be. But let's run through a more quantifiable example here. Let me turn on Top Hat. So let's see. I think it should be this. Yeah. Okay, so in terms of understanding the phase diagram, for this particular one, it's copper and nickel. If you're given this phase diagram, what can you say about the solution? So if you're at 35 weight percent of nickel, can you say that it's a solid solution of nickel and copper with the atoms randomly dispersed throughout the same crystal structure? That's A. Can you say that it's nickel with copper precipitates throughout, or can you say that it's copper with nickel precipitates throughout the solution? You're welcome to talk to your neighbor and consult, by the way. What is the what? Oh, I'm sorry. Okay. Oh, I don't think I activate the wrong one. What is the alpha phase? Is what it should have said. Sorry. Sorry about that. Didn't get translate to Top Hat properly. Yeah, Kevin. let's pick this up, but
So
yeah, I get you.
the one question I have is,
Yeah.
what does it mean by the alpha phase? Does it mean the straight alpha phase or the L plus alpha?
No, I mean straight alpha,
Okay.
just alpha. Okay, all right. One last question before we discuss it as a class.
Oh, yeah, I just had a question about the lever kind of thing
Yeah.
you were saying. So it doesn't make sense to me that it's actually closer to the liquid, like vertically, than it is to the alpha phase.
Consider only horizontal. Ignore the vertical. Okay, we'll talk about that, but thanks for bringing up the next point. You guys are really good at segues. Okay, let's discuss it as a course, as a class, because I want us to talk about this together. Okay, 3 more people. Please put in your answer so you can be logged. I'm going to count down to 5, from 5, and then we're going to go ahead and discuss as a class, okay? 5, 4, 3, 2. If you're having logging issues, you know who to email by this time, okay? Okay. Wow, we lost the person. Ooh. Talk about drop. Okay. All right, so there's a good majority that said that is a solid solution of nickel and copper with atoms randomly dispersed throughout the same crystal structure. It is not precipitates, because precipitates indicates that there's a cluster of, let's say, nickel in copper or copper in nickel, and that's actually a whole completely different situation. Potentially a whole different phase if we're talking about that. And why this doesn't happen is because of the Hume-Raudry rules, right? It doesn't happen because nickel and copper mix well together. They form solid solutions. So you're typically not going to get like clumps of nickel in a sea of copper because they're just going to be randomly mixed. They mix very well. Obviously, we're going to be talking about examples where you want that. You will induce precipitates for strengthening mechanisms, but in this case, they will form a solid solution. Yeah?
What would be a phase of an example where you would have precipitates?
Oh, well, anything. Anything that doesn't form a solid solution. So even iron carbon, right, steels. At a certain point, we'll be talking about steels where you add in up to 0.76 weight% of carbon. After that, you're going to get Fe3C, right? It doesn't really mix in. It forms a whole nother phase. But there, right? So when you have limited solubility, when you reach that point and you go beyond, things are going to start crashing out because it says energetically, it doesn't make sense for me to mix in with you. I can accommodate up until a second component up until a certain point, but after that, I'm just going to stick with my neighbors. So if you've taken thermodynamics either in MECI or CBE or even chemistry, you'll discuss these topics where, you know, if A plus B, are you going to get random mixtures of A and B? Or are all the A's going to stick together because it's energetically favorable for them to do so? That's when you get that example. Yeah, so iron carbon is one of them. And basically anything that doesn't satisfy the Hume-Raudry rules, which is like the majority of real life materials, that is going to happen. So if you just increase your steels and just say you dump in carbon, you just like burn it in CO or CO2, like just keep on going, eventually you're going to get graphite. And then the graphite is just going to cluster together. It forms precipitates, and it's going to say, I don't want to hang out with the iron anymore. I'm just going to hang out with other carbon and start making graphite. And then you increase the pressure, you're going to get diamond. So yeah, it's all energetics. Basically, any other real life material is the answer to your question. Okay. So voila, we've discussed that. There was a question in the front about the vertical line. The vertical line is just for a visual guide to the composition. If you're given a composition, let's say I keep at this 35 weight% because it's a nice in the middle, and so it's very easy for me to make very oversized dots for you to see. If you choose 35 weight%, all that vertical line is telling you is that you're dropping in temperature. That's all it's telling you, okay? When you're doing the tie line, only look at the horizontal line. So here you're at 1250 C, only look at the line that's at 1250 C all throughout the different compositions, okay? Okay, so in the interest of time, let's go through the quantitative, because I want to reserve enough time to actually walk through the numbers with you. Okay, let's go back to this lever rule situation where I want to say, okay, some amount is liquid, some amount is solid, or vice versa, right? Depending on where your liquid is. We've oriented it so that it looks like that. So it's saying some component is liquid, some component is solid. Here we call it alpha. What is the quantifiable amount? What is the weight fraction of that phase? So I'm not talking about compositional fraction. That's 35 weight percent nickel, 65 weight percent copper. Now I'm saying at this composition and at this temperature, what is the phase weight fraction? So how much liquid versus how much solid, or how much alpha is there? So you apply the lever rule. And the way you do that is you treat the tie line like so. Okay, so if you're given this composition, you draw your tie line until it hits the solidus, and you draw your tie line until it hits the liquidus, and then you say, okay, what's the composition? So this is atomic composition or weight composition of each component, right? And we call that the composition at the liquidus line C sub L. The composition of right at the solidus is C sub alpha. And so if you want to know what is the weight fraction, how much liquid is in there versus how much solid, how much has it solidified so far, you apply the lever rule. And you just say, okay, well, if I want to know how much liquid is in there, I take this y and divide it by the total. And that's what's shown here, y divided by x plus y. If I want to know how much solid is in there, well, it all has to add up to 1 or 100, right? Well, it's fractions, so it has to add up to 1. So you could just do y minus that, or you can independently calculate that fraction, and together they should add to 1, and that's your sanity check. So you can do an independent calculation and say, okay, well, I want to know how much solid is there, so that's x here, divided by the total, so that's x plus y, that's the length, okay? So what are these values? What is the length? Well, the whole length is C alpha minus C sub L. Okay, so this right here, obviously there aren't like tiny little grid lines, but that's estimated to be about 44 weight percent of nickel. And where the tie line touches the liquidus line is about 31, 32. Okay, if you're just eyeballing, this is how you would do it. So it's then you plug those numbers in, and y is this right here. So that's C alpha minus C naught. C naught is always defined as the composition that you're at. Okay, so let's do an example. Okay, this is the derivation. I'm not going to go into the derivation in class, but you have it in your lecture notes, so you can sit down and just go through it. It's just algebra. I switch things back and forth to get the final working equations for you. Okay, but in the interest of time, so that we can do an example together in class, I want to do it together. Okay, so here's the example again. 35 weight percent. You have to know your composition. What are you working with? What's the material you just gave me? Okay, it's 35 weight percent nickel. Thus, the balance is 65 weight percent copper. That's what these numbers mean. And I asked you, okay, at 1250 C, there's going to be first of all, how many phases are there? You got to know that. So you just go down this table. So if you set up this table for yourself, you say, okay, I know I have some liquid and solid. My liquidus, here I've actually worked it out to 31.5 weight percent nickel. The composition of right at the solidus, if you trace it down, it's at 42.5, okay? So then the phase weight fraction, how much liquid is in there, is C alpha, so here's C alpha, minus C naught, that's the composition that we're working with, over the entire length. So here is 42.5, CL is 31.5, and your C naught is 35. So the total, x plus y, is this length. And so the difference is C alpha 42.5 minus 31.5, so that's your entire length. The amount of liquid that is in existence right at this temperature is this, Y, 42.5 minus your composition, which is 35 right there. Okay. So then you could say the same thing. Okay, how much is solid? How much is alpha? Well, that's C naught minus CL, so 35 minus 31.5 over the same distance, because it's fraction, and that gets you 32. So you could do these two calculations independently, but 0.68 and 0.32 should really add up to 1, right? You could have just stopped after doing this calculation and said, well, the amount of solid is just 1 minus liquid, because it has to add up to 1. So I'm not even going to bother doing the second calculation. Or you could do the second calculation and do your sanity check and say, yeah, okay, 0.68 adds 0.32 is 1. Great. So that's how you would quantify it. And you do this approach for every single temperature and every single phase. If you have a two-phase region, a two-phase phase field, this is how you apply the lever rule to get the amount of liquid versus the amount of solid that you have. If you have solid, same diff. If you have solid 1 versus solid 2, lever rule is going to take you far. Okay? Okay, I want to reserve time for any questions or clarification, any follow-up. Did I answer your question about the vertical versus horizontal-ish? Okay, we can talk after class if it's not clear yet. Question? Oh, so the question in the front was, when you're doing a problem like this, why are you using the weight percent of nickel versus copper? It doesn't really matter. I mean, the x-axis, as you can tell, is in weight percent of nickel. So this is increasing nickel weight percent. If I had it flipped, it doesn't really matter. It's the same, because your numbers are going to be 100 minus that, or 1 minus that. So there's no difference. Question?
So in this instance, again, if we would have gone with the 65% weight of copper,
Mm-hmm.
it would have just been all solid.
Wait, what?
If we would have went with the 65% weight of copper and just moved the lever over to 65% at 25 or 1250 degrees, it would have just been all solid.
No, you would be at the same place. It's just your phase diagram is going to be the mirror. Your x-axis, see, you're changing your x-axis now.
Right.
Yeah, so you have to flip all the other values as well. Okay. I just worked with nickel, see? Yeah, okay. All right, lecture is adjourned, but I will continue taking questions.